Thank you very much, Mr. Chairman, and thank you very much for inviting me today. It is a pleasure to be here. And thank you also for Professor Mang for showing how much he collaborated in the last 40 years. And I was born a few years after diplomatic relationships started. And for me, it has always existed. China and Austria working together. So, and I had the pleasure to visit China twice. I have seen it in '99 and in 2008, and I have also seen how quickly and how incredibly the development is in China and how fast things develop. So it's a pleasure to collaborate again and to have this project now with a Chinese company, and I'm happy that I can present you my work. So I would like to talk about virtual and augmented reality research at Technical University in Vienna. And at the moment, I hope you can all see my screen. Yes. At the moment, I have a group of about 10 students, 4 postdocs and 5 PhDs, and I'm heading the group. And we do research in the whole area of virtual and augmented reality, and that is quite big. But before I talk about the different projects and work that we do, I would like to explain what is virtual reality and what is augmented reality. And therefore, I have to refer to Paul Milgram. Mr. Milgram, in 1994, he defined the so-called mixed reality continuum. And on the one end of the continuum, you have reality. And on the other end of the continuum, you have a virtual environment where everything you see, everything you smell, everything you feel, everything you hear is virtual. For example, the vision here would be the holodeck from Star Trek. You probably know, where people can walk into a virtual environment and everything is virtual. So this is on the other end, this is virtual reality. And in between, we have a lot of mixtures between reality and virtuality. And all these mixtures of real and virtual are mixed reality. Nowadays in the media, you sometimes hear the term XR, extended reality, and so on. This is all mixed reality. There are mixtures of real and virtual, and some of these mixtures, which are closer to reality, are called augmented reality. And augmented reality is defined as a combination of real and virtual. It is always interactive, which means you can do something. You cannot just watch the virtual experience, you can interact, you can do. And the real and the virtual objects are registered to each other in 3D. So when you're looking at a washing machine and you see instructions through your glasses, you know exactly the position of the washing machine or of the car, and you can overlay information over that object. You see some examples here. The person is holding a marker here, and the glasses overlay something on this marker, or here you are driving and you see a heads-up display and some overlay over this display. So you need to know the position of the real objects and the position of people. And these 3 aspects define augmented reality. And when we are working in virtual and augmented reality, we always have to deal with a couple of problems with multiple aspects that are always involved. So on the outside, you can see different projects that we did. We did projects in the medical domain, for firefighters, for training, all kinds of different industrial projects that we did. And we always have to deal with these aspects, with rendering and viewing. How do I display something on the head-mounted display or on a mobile device? How can I localize people very precisely? Nowadays, we have methods inside a room. We can have millimeter, sub-millimeter precision, and we can track moving objects very precisely. We also want to have that outside all over the world in very high precision, if possible. Then we have to deal with interaction. How can we interact with this virtual world? How can we collaborate with others? 2 people, more people? How can we work together between Austria and China, all in the same virtual space? And how can we distribute over network? How can we send big virtual worlds over network and work together? And then the most expensive part of a virtual reality experience is creating the content. The hardware is not so expensive anymore. You can buy very cheap head-mounted displays and very cheap hardware, but content generation, building these virtual worlds, modeling everything, that's the most expensive part. So we are doing research, how can we do the modeling in an automated way that we don't need 100 engineers who are modeling and building, that we can auto-generate large virtual environments. This is research in authoring. And then, of course, the user is involved. So wherever we work in virtual environments, there are users, and users perceive these things. How do they perceive them? How do they see space? How do they feel in these environments? This is the area of perception. And what I would like to present you now is work that we did in the area of large-scale virtual environments where we can freely walk around, and also about haptics, how we can touch things in large-scale virtual environments. This is research where we do a lot of projects at the moment. So let me motivate this topic. Did you ever want to walk through the pyramids, maybe inside? Or did you want to walk through the Guggenheim Museum and see all this art? Or walk through Eremitage in St. Petersburg and see all this beautiful art? Or maybe you want to walk on the Great Wall. What about doing all of that in one day? You might say, well, walking through all of these places in one day, that might be a bit difficult. Well, in reality, it is very difficult, if not impossible. But if we simulate these large virtual environments in a virtual world, then we can really walk through these large virtual environments. So what we want to do is real walking in virtual environments, in large virtual worlds. Why don't we just sit on the computer screen and use a controller, a joystick, and move back and forth? Well, yes, you can do that, but many studies have shown that if you can walk and really use your body to move around, it enhances the sense of presence. You feel more present. You can perceive size and distance is much better if you really walk with your body through environments. You can focus your attention on what is important, and it also improves your performance, your task performance. So we have this lab at our university where we can experiment and test walking through large worlds. And we did, and this was already, and we developed a platform already 7 years ago now. We developed a virtual reality platform, and we did a couple of studies with it to see how we can study how users interact in such environments. And here in this study, we tested if users, if they are really immersed in a virtual environment, if they notice other users in this environment, they can only see, I will show you a brief video so you understand what I'm explaining. So we have two users, and these users have to walk here. And the user just sees a bird which is flying in front of him, and the user has to walk through this environment. And we tell the user, if you notice that someone else is here next to you, then just point with your finger to that person. So the user is walking now in this virtual environment. He sees the bird. And we have another user who is also walking. And they are very close to each other. And you can see this user has noticed the other one, he's pointing to him. But now we have two users who walk very close. They don't notice anything. Here again, nobody noticed the other one. Here they get very close, and sometimes users even touch each other, and they don't notice that there is another person. They are not aware of it. They are so focused and so immersed in this virtual environment that they don't realize what's going on around them. And from 36 participants, only 6 people noticed someone else. So when we saw this and when we tested it, it was clear we need algorithms for collision prevention. We must make users aware that there is someone, otherwise they simply collide and they don't notice. So in the next step, we developed a platform for a game company in Germany, Illusionwalk, and you can see here how this platform looks, and people are immersed and can work with gestures here in this in this environment, and they can play games together, multiple users. It's used for multi-user gaming. They can walk around. It uses a very low-cost tracking system that we have developed ourselves to locate people in this environment. And we have an elevator where you step on and then it rumbles and you think you're going up into another floor. In reality, you are just at the same place. And you can also touch objects. And this kind of technology can not only be used for gaming, but we also use it a lot now for training. Training first responders, medical training, also military training, where multiple people have to work together and learn some tasks. We also use this platform for large-scale visualization. We just had a paper in Nature Communications where we developed a protein network together with biologists and visualized a large protein network where you can walk through. It can be used for architectural design and visualization, also in the construction industry, of course, that you can see large-scale models of things and walk around. And we use it also for a food production company. They are producing very large machines, baking ovens, which are 20, 30 meters long. And when they try to sell these machines, they cannot put them all in a hall to show them because they have so many and it would be just too much to show all of it. So we designed a virtual showroom for them where clients can walk around and see the different machines and try configurations. It can also be used for rehabilitation and therapy, for virtual tourism, as I said in the beginning, to visit the Great Wall from home, and virtual museums. So what I showed you, the problem here is that our movement is limited to the space that we have available. So we just have 140 square meters here in our lab. What if we want to walk through a large cathedral? It might get a bit tight. So how can we make users believe to walk in a much larger space? For that purpose, 15 years ago, so-called redirected walking techniques were invented. With redirected walking, you move users without them noticing. So, for example, when a user is walking to a wall here, you see the path of a user, the user walks to a wall, then the user has to turn around, of course. But while the user thinks he is turning around just 90 degrees, because in the virtual environment, he sees a rotation of 90 degrees. But in reality, you make him turn around 180 degrees. So the user is turning around much more and more, but in the virtual environment, it's rotating much slower. So he doesn't notice that he's rotating much further in the virtual, in the real world. And this is called rotational gains. Then you can also do translational gains. When the user is making a step, you make the step a little bit larger or a little bit shorter. So you can manipulate the movement of the user and the user doesn't notice. In this environment here down there, we see the user thinks he's walking this S-shaped path, and in reality, the user is walking always in this 8 figure. The user doesn't notice. There are other psychological phenomena that you can use, for example, change blindness. A user is walking along a corridor, is entering a room and has to fulfill a task here. For example, on the sofa is a book. He has to pick up the book and then leave the room. So the user enters, is focused to do the task. And when he turns around, the door is suddenly on the other side. And the user doesn't notice. He was focused on the task. He walks out and the movement was redirected. He's moving now in a different direction. Or here, impossible spaces, a user is in one room, and when he walks out the corridor and walks into the next room, suddenly the next room gets larger, and the user thinks he is in 2 rooms of the same size. And when you ask users afterwards if they notice anything, most users don't notice that there is a large overlap of these 2 virtual rooms. And based on these findings, we developed our own method called flexible spaces, where we also use the disorientation of users. So in this, experiment, you see a user entering a virtual room. And on the right side here, you can see the top view. So the user is now in this room. And here on top, you see the real environment where the user is walking around. It's a 9x9 meter environment where the user can freely walk. And the user is in this virtual environment. And when the user is leaving the room now through the door, a corridor is generated. You see that here. The user is walking along the corridor and he gets to a second room. And this second room overlaps with the first room. But the user is moving along two corners here. And the user doesn't notice that there is an overlap and he gets into the next room and so on and so forth. So when you ask users afterwards, how big was the space where you moved around? Then they draw up a very large map where they moved and walked, and they do not realize that they have walked in a rather limited space with lots of overlaps. So this is an interesting phenomenon that we discovered, and my student is currently finishing her PhD thesis about this. We also studied different corridors and how we can make users believe to walk in even larger spaces. This method now creates corridors procedurally. It can also be used outdoors, of course. What you see here are very simple spaces. You can make this much more beautiful, but for research purposes, we used very simple environments. Outdoors, for example, you can use hedges and paths, and then you move the sun and trick the user by different positions of the sun and so on. And the real world rules do not apply here. You cannot construct these spaces. These are not architectural spaces. These are purely virtual spaces, but this works if you focus on virtual content. For example, if you use this for art exhibitions, then you can put different art in these rooms and people don't care how the rooms are connected. They are focused on seeing the art. Or for games, of course, you can use it. Now, we know now that we can walk through virtual environments, and we also know that we can create virtual content in virtual environments. So here, for example, this is one of my early works nearly 20 years ago. You can model in 3D in virtual environments. And nowadays, you know, most of the production processes are virtual production processes. Everything is produced first on the computer. So, but what if you not only want to see objects in a virtual environment? What if you really want to touch them, feel them, see how the mechanical properties of these objects are? For that, we need haptics. And what we are looking at is to provide the user with haptic feedback in large virtual environments where they can freely walk around. So in the top image, you see a first experiment we did nearly 5 years ago with a very simple robotic arm. And when the user wants to touch a wall, the robot is presenting a piece of that wall at the correct location, and the user is touching this wall and thinks there is a real wall. Whenever the user is touching, the piece of wood is at the right position. And now we are looking to do this in a large environment. We have an 8-year project running at the moment where we are using this mobile robot here. You see him, you see the robot here. It's a cobot, a collaborative robot. And this is your personal assistant. This robot follows you through the environment. And whenever you want to touch something, the robot will present you a piece of wall or a piece of object, whatever you need in the virtual environment. Important here is to do this safely. Of course, the robot has to be very fast to follow you because you are walking through this environment. The robot must be there before you, but it must be safe, and the system must anticipate your interactions, maybe even support multiple users and be at the right place at the right time. So here you can see now our robot moving around. Here it's remotely controlled, but at the moment we are working on it, programming it to do everything automatically. It has omni wheels. It can move in every direction at any time, which is important so that it can move out of the way when the user is walking to it. and it has sensors to detect if there is collision. It's a copod, so it stops if there is collision. And this is such a typical scenario, a wooden board, for example, in front, that is mounted in front here. And you must be aware that the user would wear head-mounted displays. So the user would wear glasses here. The user wouldn't even see the robot. The user would not hear and would not see the robot. He is immersed in a virtual environment, and the robot is just moving at the right place and presenting the user with objects that he wants to touch. So, and if the user walks to the robot, he must quickly move out of the way. So, challenges are to react to such unexpected user movements. Users are unpredictable. We have close direct interaction with the robot. We cannot adhere to these standard safety measures in robotics. For example, one of the ISO norms is that the robot is only allowed to move 1.5 meters per second. This would be too slow for us because the user must be able to get out of the way quickly when we move through it. If it slowly moves with 1.5 meters, we would run into the robot. So it would not be safe. And what I didn't mention yet, we are collaborating with the Mechanics Institute, and we want to simulate material properties. So when the user, for example, I've shown you this surface here, this winglet from an Austrian company, and this is elastic to some degree. And when the user wants to touch such a surface, the robot should simulate correctly the elastic properties so you can really feel how this material reacts to your touch. This is also part of our research. In summary, we want to enlarge walkable spaces. We want to allow multiple users to walk freely, avoid collisions in large environments that are distributed over network, so that they can interact with objects and get haptic feedback. Thank you very much.
Thank you, Professor Kaufmann. Very interesting presentation. And Professor Yuan said in the chat that positioning in closed space is always a challenge to people. The technology would benefit not only for people in a room, but underground space at the terminal. So
yes, that's of course. Yes, of course. Yes.
I would like to ask you, because I'm also a geotechnical engineer, do you have any cooperation with the construction companies?
Yes, we have one project. We had one project where I even have a slide here. We had one project with a construction company. You see here, the problem is in underground spaces. For example, this is just the basement of a building. And sometimes you want to do augmented reality in such spaces. But for augmented reality, the augmented reality classes are using cameras to locate the user. They look into the environment and detect features, corners, edges of objects, and they try to track the user based on these features. But the problem is, in some of these new spaces, there are white walls. You don't have features. There is no color. There are no features. So what we did is we developed a laser projector, which is projecting a laser pattern onto the ceiling. So you create your own features. And then they had the augmented reality glasses, HoloLens, for example. They can work in such an environment because they can see more features. So this is one of the projects where we have been involved. And now we are also starting a project with a construction company for BIM models, building information modeling, because the problem here is that the real building and the BIM model are never identical. So what has been built is always a little bit different to the model, and we try to automatically find the differences. So we do a laser scan and have an autonomous process to detect differences in the real building with augmented reality, and then move it back to the building, to the BIM model. Thank you for the question.
Any other questions from the audience? This is it's a little late in China, like already
Yes,
11
yes.
p.m. in China.
Professor Wang's conclusion would have been much better for this forum because he presented so beautiful pictures of the development of China.
Yeah, I was hoping maybe for the next anniversary, 60 years anniversary, maybe we can have this meeting with the virtual reality. That will be much cooler.
Yes.
We
And
don't
I
need
hope
to
we
worry
can,
about the coronavirus.
yeah, I can hope we can meet in real again sometime. But thank you for inviting me, and it was a pleasure to be here, and thanks.